Okay, in the last video we finished off by looking at the notion of expected return and how we might come up with that number by looking at historical returns, that is a series of returns, and then also using scenario analysis. So let's move on and take a look at measuring risk. One way to think about risk is to consider how much uncertainty there is in the outcome. So uncertainty and risk are very good synonyms. We're going to look at one measure of risk, and that is the standard deviation measure, square root of variance, so these things are exactly related. And it's a measure of the dispersion of the possible outcomes, and the way we interpret that is the higher the number, the more uncertainty, the more risk there is. So we can do standard deviations of both of those measures of expected returns that we just looked at. With the time series of returns, it's very simple. We can just use the sample standard deviation, and in Excel, it's just the standard deviation of a sample function. So it's a very simple thing to do, and we'll look at that in the spreadsheet in a second. The scenario analysis is a little bit more complicated, and this is going to be kind of like an old-fashioned way of calculating standard deviation and variance. There's no function that you can use in Excel. You're going to have to kind of use Excel to do the math, do the statistics that you would have learned in an introductory statistics class to figure out the standard deviation. So what we're going to be doing is coming up with a probability weighted sum of squared deviations. And we'll look at how to do that right now in Excel. So let's go back to Excel, to that spreadsheet that we were looking at before. And now we're going to look at the standard deviations. So these numbers here, and then this calculation over here on the right. So with standard deviation, we're just going to use, as I mentioned, the standard deviation function, and we highlight the cells that we want to find the standard deviation of. So if we look at the 2-year average returns, we have a 12.02% average for those 2 years, and the standard deviation is a measure of how far apart those two returns are. So if you look at them, they're actually quite close, 11.32 and 12.71. There's a pretty tight spread there to get that average of 12.02. Similarly, with the 5-year returns, the 5-year average, if you look at those 5 years, again the return spread is pretty tight. We got a range all the way from 10.15 to 13, but they're all in double digits. They're all in kind of that same range. And so our standard deviation is relatively small, 1.4% for those 5 years. Now if we include 10 years, we get a little bit more variety. We've got all the way down to negative 17, almost negative 18% in 2009, all the way up to about 16% in 2006. So our average is 7.72, but our standard deviation has jumped up quite dramatically. And again, if I look at how to calculate that, it's relatively straightforward. I just highlight those 10 years. So that's very straightforward to calculate standard deviations of a time series of returns. Now we want to come up with a measure of the standard deviation for this scenario analysis. It's just a little bit more involved. So the starting point, and we're going to be over here on the right-hand side. The starting point is computing the expected return. So we went through that in the last video. And so the next question in determining the variance in the standard deviation is to see how far away we are from the expected return in each of these scenarios. And so that's what this column is doing here, where I have the deviation from the mean, column 4. And if you look at the formula, it's just the return for that scenario, and then we're going to subtract from that the expected return over all of the scenarios. Okay, so that's the deviation or the difference from the mean. In the case of a depression, we're 75.96% below the expected return over all of the scenarios. So if we have a negative 70 and the expected return over all of the scenarios is a positive 5.96, then we would be 75% below the mean return or the expected return. Those are synonymous if we were in a depression. Same thing with the deep recession. We would be 30.96% below. And let's look at the formula again. It's the return for that scenario, subtract out the expected return over all of the scenarios. So I'm going to copy this formula all the way down, and if we look at this last one, again it's the same idea. With a boom, we're going to be a little over 60% above the expected return if we find ourselves in that scenario. So first thing is find this deviation for the mean. The next column is we're going to square that number. So I'm just multiplying that fourth column, the deviation from the mean column, by itself here. It's a squared deviation. It forces everything to become positive. So again, same formula all the way down, the number times itself. And then the last step, actually I shouldn't say that, is the second to last step. We're going to multiply that squared deviation by the weight for that scenario. So we've got the squared deviation for the scenario, that's in this column. We're going to multiply it by the weight or the probability of that scenario. So that's what's happening in column 6. I'm multiplying column 1 times column 5, and I've got this number go all the way down, and then we're going to add each of these pieces. That's going to give us the variance. It's a measure of how far all of these returns are on a weighted basis, and then we're going to just simply take the square root of the variance to get the standard deviation. So in this particular case, I've got 17.36%. Let's just do a couple of things here. I'm going to change a couple of weights and make this thing a little bit more spread out. If you look at the probabilities, most of the mass, most of the weight is in these middle sections. The mild recession, the stagnant growth, the normal growth. The returns are relatively tighter. But if I put more weight or more mass in these extremities, then I'm going to have a much bigger standard deviation. So let's just see what happens here. If I say the possibility or the probability of a recession is 10%, and I drop down the probability of a mild recession to 11%, drop this to 30, drop this to 25, and then my boom also has a pretty big probability. Look what's happened to my standard deviation. I've almost doubled it by moving more mass out to those extremities. The depression and the boom have the biggest variance or the biggest difference from the average return. So that's what's driving the standard deviation. We're looking at all of these things, how they're spread out, and in the case of the scenario analysis, where the weight is, where the probabilities are. So that's how to calculate the standard deviation across a couple of examples, one with a time series of return, very simple, just use an Excel function. And then with scenario analysis, we're going to use kind of a mathematical construct and build up the computation. Let's keep moving here and take a look at relating risk and return. So returns, and especially expected returns and risks, should never be considered in isolation. They're always together. I've heard it said that they are married, return and risk, so they're always going to be together, and you always have to consider one with the other. So another way of saying that is that not all 6% returns are equal. If there is a higher volatility associated with one of those assets or one of those sets of returns, it's going to be less desirable than alternatives that have lower risk or lower volatility. And then we could look at expected returns as it being a function of risk, and this is a very kind of common way of expressing expected returns, where we have the expected return at time t is equal to the risk-free rate, that's the RF, at time t, plus an expected an expected risk premium. So where the risk premium is going up as you add more risk to an investment. So this is just a very explicit way of saying the more risk, the higher the expected return should be. If risk goes up, the risk premium will go up, and so your expected return will go up. All right, let's look at one more very common measure of return we're going to use quite a bit in this class, and that's the IRR function. And then we're also going to add to that the XIRR function. So the XIRR is actually probably a better function to use, and it takes into account the dates, the specific dates. The IRR function assumes that every cash flow that you have has an equal interval. There's the same space of time between each of those cash flows. But frequently, reality does not work just like that. We may have a cash flow that happens every quarter for a couple of quarters, and then we have to wait 5 months, and then we wait a year to get another cash flow, and then we have a series of monthly cash flows. So frequently, reality is much messier, and so that's what the XIRR function is capable of doing, is taking that into account and giving us an accurate aggregate return or an aggregate geometric rate of return. So let's take a look at the IRR function in Excel and the XIRR. So over here on the right, we're going to take a look at the IRR function and the XIRR function. And with the IRR, we need to have, up front, we're going to want to have our initial investment, and then we're going to follow that by a series of periodic cash flows. In this case, I've labeled them as annual cash flows. And then we're just going to use the IRR function, very simple, very straightforward, highlight all of the cash flows, and we would get an internal rate of return. With the XIRR, the new argument that we need is a series of dates. So if you look here, I've got a series of dates and they're not equally dispersed. The first date is separated by 2 years from the second date, and then we have a series of future cash flows that are bouncing all around. And again, this is a picture of what a real estate investment might look like. We've got cash flows that are happening at different intervals. And so for the XIRR function, what we're going to do, and it tells you, by the way, when you do the XIRR, we need the values first. That's the first set of arguments separated by a comma with the dates. And so that's what I've done here. And the interpretation of the XIRR is important. This is going to be an annual rate of return. Even though we've got different periods, different intervals, this is going to be a geometric average rate of return. So just like we calculated over here, Excel does that for us with these dates, and we've got 2.934%. And just real quickly, let me show you how the XIRR relates to the geometric mean here. Let's say that I started my investment over in this column D in 2001, and I'm going to invest $1,000. Now let's see how long it takes me to end up with this $1,689. So this is the end of the first year. This would be the end of the second, end of the third, 4, 5, 6, 7, 8, 9, 10. So 10 years total. So end of 10 years would be 12/31/2010. So that's 10 years after that January 1st, 2001. If I link to this cell, this little series of dates and numbers says that I invest $1,000 at January 1st, 2001, and then I end up with, or I get back, $1,689 after those 10 years. So with the XIRR function, I can get that same number, or very close. So I highlight the values, I highlight the dates, and I expand my, get my number, 5.381. It's off by 0.002, so 2/1000ths of a percent. And the reason is because this function right here is counting days, and we've got an extra leap day in there somewhere. So if I change this to 12/30/2010, I get the exact same answer. So regardless, they're super close, and that's what the XIRR function is returning you, the answer you're getting. It's a geometric mean based on the dates and the cash flows that you're feeding it. So it's an important function, and it's one that I'll ask you about on a test. So that's all for, let's just make sure here, that's all for the risk and return measures, and I'll see you next time.